So in the last video we have discussed about the biological factors affecting oral drug absorption. Today we are going to discuss about the physicochemical properties of drug, how it is going to affect the oral drug absorption. That is the properties of drug. Earlier we discussed about how body is affecting the oral drug absorption. Now we have to discuss how the drug is going to affect the oral drug absorption. So what are the properties of the drug that are going to affect the oral drug absorption? Drug, when it is given in the form of solid state, the drug first of all must undergo dissolution and the drug will be now in solution, and then the drug permeates through the membrane, that is absorption takes place, and the drug will be in systemic circulation. So if the drug is given in the form of solid state, that is tablet, capsule, suspension, powder, any other solid forms, the drug must first undergo dissolution and they have to go into solution state, and then they must absorb and enters the systemic circulation. So there are some two rate limiting steps are there for drug absorption. What is now rate limiting step? Rate limiting step is nothing but the slowest step of absorption. So the absorption will be affected by two steps, either by dissolution or by absorption. So the rate limiting step can be dissolution or absorption. Rate limiting step is the slowest step of the drug absorption. So absorption will be delayed because of either dissolution or absorption. So when the dissolution will be rate limited, when the drug is having low solubility. So when the drug is having low solubility, then the dissolution of drug will get delayed, and the drug which is having low solubility has high permeability because they will be lipophilic in nature, whereas the drug with high solubility may dissolve faster, but as it is lipophilic, hydrophilic in nature, they may not permeate through the membrane. Hydrophilic materials have difficulty in permeation through the biological membrane. So absorption will be rate limiting step for high soluble drugs, whereas dissolution will be the rate limiting step for low soluble drugs. So the rate limiting steps may be either dissolution or absorption. It depends upon the solubility of drug. High solubility will have absorption rate limited. Low solubility will have dissolution rate limited steps. Now the drug before absorbing must dissolve. So when the drug is in solid state, there are some factors which are going to affect the oral drug absorption, like dissolution and pH, then diffusion layer pH, then Prodrug, if the drug is given in the form of Prodrug, surface area and particle size, then salt form of drug, and then crystalline nature of the drug. Even the stability of the drug stability also have effect on the oral drug absorption. And when the drug goes into solution, just the two factors that are going to affect the drug absorption, that is the pK of the drug and where it is placed, its pH. pK of the drug and GAPH, and the next property of the drug to be considered is lipid solubility or its lipophilicity. So these are all the factors that we have to consider before studying the physicochemical properties of the drug. These are all the physicochemical properties of the drug that are going to affect the oral drug absorption. So these are the factors when the drug is in solid state, and these two factors when the drug is in solution state. So now, initially, the first factor is dissolution and pH. So the dissolution rate of drug can be explained by the famous equation, Noyes-Whitney's equation, where the dissolution rate is equal to dAKO by W CS minus CB upon H, which is similar to that fixed law. Fixed law explains the diffusion rate, whereas Noyes-Whitney's equation explains the dissolution rate. Here, instead of C1 and C2, we have mentioned CS and CB. Now, what is the CS, CB? dC upon dt is the rate of dissolution. Now, these are all the parameters which explains the diffusion layer. Now, what is the diffusion layer? So, when the solid drug dissolves and it forms a saturated layer around its surface, which is known as diffusion layer. What is this? Diffusion layer is the saturated solution of drug. When the drug gets dissolved, the drug saturated concentration makes a layer around its surface, which is known as diffusion layer. So the concentration of drug in the diffusion layer of CS, that is saturated concentration. From this diffusion layer, the drug must diffuse and enter the bulk. Now the concentration of drug in the bulk is CB. Concentration of drug in saturated layer or the diffusion layer is CS, whereas the concentration of drug in bulk is CB. Once the drug dissolves in the concentrated layer, that is saturated layer, and diffuse through the diffusion layer and enters the bulk, it gets diluted immediately and the concentration of CB will be very less than that of CS. So you can neglect this CB from the equation, and the equation will be further reduced as K dash into CS. Now what are these parameters? D is the diffusion coefficient of the diffusion layer, A is the area of diffusion or dissolution, Ko by W is the permeability through that diffusion layer, and H is the thickness of the diffusion layer. Now the dissolution rate is inversely proportional to this diffusion layer. If the drug is having low solubility, the thickness will be greater, whereas the drug with high solubility, this layer will be very thin. Its thickness will be less in or at the surface of the drug. So these all the parameters which are saturated concentration, permeability, diffusion and area are directly proportional to the dissolution rate, whereas the thickness of the diffusion layer is inversely proportional to the dissolution rate. Now what we are discussing, the dissolution and pH. How the role of pH affects the dissolution of drug. We know already the drug which is ionized gets dissolved more. So where the ionization will be more? So when the acidic drug is placed in acidic environment, that is when the acidic drug in stomach will have unionized fraction of drug and there will be reduction in dissolution. The drug must be in ionized state to get dissolved. If there will be ionization, the drug's dissolution will be less. Whereas for basic drugs, if it is present in stomach in acidic medium will be ionized. Here the dissolution will be increased. Vice versa in case of the drug, basic drug in acidic environment, acidic drug in intestinal medium and basic drug in intestinal medium. So we considered initially stomach and then in intestine. In intestine, basic acidic drugs in intestine. Acidic drug in basic medium, ionization will be more, so it increases dissolution. Whereas basic drugs in intestine, in basic medium will be unionized, will reduce the dissolution. So what does it mean? Acidic drug will have its greater dissolution in small intestine, whereas basic drug gets dissolved more in stomach, that is gastric region, because of its ionization. This is all about dissolution and pH. So if you need to explain the theory of dissolution, you can explain by Navier-Stokes equation. Now the next factor which is affecting the drug absorption is diffusion layer pH. We were just discussing about the diffusion layer. So what was the diffusion layer? It is the saturated concentration of drug at the solid surface. This is known as diffusion layer. So what will be the pH of this layer and how it is going to affect the drug dissolution or diffusion through this layer? So consider the weakly acidic drug. When this solid drug is weakly acidic in nature, then the saturated concentration in the diffusion layer will also be acidic. So acidic in acidic environment will have unionization. So unionized drugs dissolution will be less. Whereas the drug, consider weakly basic drug, and weakly basic drug will make the saturated concentration whose pH will also be basic in nature. Again weakly basic and basic diffusion layer. So base in base will have unionization, leads to less dissolution of drug. So this is the importance of the diffusion layer pH. If the drug is weakly acidic and the diffusion layer also will be acidic in nature, because the layer is nothing but it is the dissolved concentration of drug. Drug is already acidic. When the acidic drug dissolves, this is the layer made by the drug itself. So it is an acidic drug. So the layer made by the drug will also be acidic in nature. And if the drug is basic, and the diffusion layer's pH also will be basic in nature. So acidic drug, when it diffuses through this layer, that is acidic diffusion layer, it will be unionized, so dissolution will be less. Whereas in case of basic drug, again basic diffusion layer, again the unionization will be there, their dissolution also will be less. Now you have to consider the salt form of drug. Another factor in 5th or 6th point I discussed about the salt form of drug. I mentioned here, I listed out here. So the salt form of drug can be discussed along with the diffusion layer. Why? Because now what is the salt form? If you need to make a salt of weak acid, you have to make salt with a strong base. Say for example, weakly acidic drug. You can consider the NSAID diclofenac. Diclofenac can be made as diclofenac sodium, which is made from sodium hydroxide, which is a strong base, and weakly acidic drug is diclofenac. And in case of weak base, can be made salt with strong acid. Take an example, alkaloid. All the alkaloidal drugs are basic in nature. So consider one alkaloidal drug, that is atropine, which is basic in nature. Have to make salt with atropine sulfate, that is sulfuric acid. Strong acid is used to make atropine sulfate. So in this case, how the diffusion layer pH varies. Now the salt of weak acidic drug will have the saturated solution. Once the salt form is dissolved, it forms acid plus strong base, and this strong base is the concentration that is present in the layer. This strong base, which is added to the salt form of drug, increases the pH of the diffusion layer. Here weakly acidic drug and the pH will be increased here. So here there will be increase in pH and the drug will have decrease in pH. So there will be ionization in the basic pH. Weakly acidic drug gets ionized in the basic pH of the diffusion layer and gets dissolved easily. That is why salt formation is one method to improve the solubility of drug. See, salt formation not only improves the solubility, there is an opposite effect of salt formation also. Why? The salt formation with strong acid or base will give you the improvement of solubility, whereas salt formation with some fatty acids or the fatty bases will reduce the solubility, will have the opposite effect in the solubility. We know earlier. So the diffusion layer is the main role. Here, when it is made with strong acid or base, the diffusion layer will have either increase or decrease in pH, which will enhance the dissolution. Whereas in case of fatty acid or fatty base, the diffusion layer will be of fatty layer. Then their dissolution again will be affected because of the pH of diffusion layer. So this is about the diffusion layer pH and salt form of drug. Now the next factor which affects the dissolution of drug is prodrug. So what is prodrug? Prodrug is the inactive form of drug. So prodrug is nothing but the inactive form of drug or the precursor which will convert into active drug in their site of action. So why we have to prefer this prodrug? Generally to increase the lipid solubility, that is to increase the permeability or to mask the bitter taste of drug, we can go for the prodrug, or to improve the stability. Generally for solubility, stability and to mask the bitter taste, we prefer prodrug formation. So this prodrug must undergo metabolism or bioactivation to convert into its active form of drug. This prodrug also will have effect in the lipid solubility. For example, chlorazepate is the prodrug which is of lipid soluble drug, which is the prodrug of nordiazepam. The sedative hypnotic nordiazepam has minimum solubility. To enhance its solubility, its prodrug is formed, that is chlorazepate. So this is about the prodrug form, how it is going to affect the drug absorption. Now the other factor which are going to affect the oral drug absorption and when the drug is in solid state is surface area and its particle size. Particle size has its pronounced effect in the oral drug absorption. So smaller the particle size, that is micronized, means micro-sized particles. Micronized particle will have increased dissolution. Is it so always? No. Always when you just consider to increase the solubility, if you discuss with the students, they will say we have to reduce the particle size. This is not always going to happen, because increase in reduction in particle size will further increase the surface area and will increase the dissolution, but not in all cases. In case of hydrophobic drugs, this will have the reversal effect, that is increase in particle size will develop static charges and it will reduce the surface area. It will not increase the surface area. There you have to increase the effective surface area. So generally micronization will increase the dissolution, that is particle size reduction. Reduction in particle size will increase the surface area, thereby it increase the dissolution. Whereas in case of hydrophobic drugs which are not soluble, decrease in particle size will lead to decrease in surface area, because they develop static charges at the surface and they tend to agglomerate. Again they will aggregate and they will reduce the surface area as its free energy is higher. To reduce the free energy, they will accumulate again. They will reduce their surface area and there will be no use of increase in surface area or reduction in particle surface. They are going to agglomerate again. So here you have to increase the effective surface area. Now how to enhance this effective surface area? So you must know what is effective surface area. What is effective surface area? The surface area of the particle which are exposed to the dissolution medium. So the medium which are exposed to the area which are exposed to the medium will only be dissolved. So you have to expose the surface of the solid to the dissolution medium for enhancing the dissolution. So how to enhance this effective surface area? By addition of some wetting agents like surfactants can be added, or you can go for some carriers, hydrophilic, mainly hydrophilic carriers like PEG, polyethylene glycol, PVP. These all can be added to enhance or to increase the effective surface area. So in case of hydrophobic drugs, simply reduction or micronization will not going to help. Further, you have to include some wetting agents like surfactants and carriers like PEG or polymers, PEG or polyvinyl pyrrolidone can be added to increase the effective surface area. So we discussed that micronization will increase the dissolution. So is there any effect? How it is there any proof or evidence that it has increased the oral drug absorption? Yes, the example is griseofulvin. The drug griseofulvin, as already I discussed in biological factor, this is highly lipophilic drug and this has dose of about 1 gram. 1 gram of drug have to be administered. Even then its bioavailability is very low. So to improve the bioavailability of the drug, we can try for the micronization. So in market, the marketed formulation of griseofulvin has prepared or formulated with micronization. If you see that micronized particle of the griseofulvin, its dose has been reduced to 1/2. That is about 500 gram of dose will be sufficient when you use micronized griseofulvin than that of the normal griseofulvin. That means when you reduce the particle size of particle size of griseofulvin, it reduces the dose. That is, the bioavailability has been achieved in the half of the dose of griseofulvin. So that is the effect of surface area and particle size. Let's move on to the next factor. When the drug is in solid state is the crystalline nature of the drug. This also has the main effect in the drug absorption when it is given through oral route. The crystalline nature of the drug. Some drug may exist in more than one crystalline forms. That phenomena is known as polymorphism. The drug may exist in more than one crystalline form or crystalline and amorphous form. Say for example A, B, C, like in case of chloramphenicol palmitate. The antibiotic chloramphenicol palmitate exists in 3 crystalline forms and 1 amorphous form. So what is this polymorphic forms? They are similar in structure. Chemically they are similar, but they are different in their physical properties. That is, melting point may be different, density will be different for these drugs, and XRD patterns will be different. That is, X-ray diffraction will be different in all the different forms. Then its solubility, stability and the therapeutic activity will be different in all the polymorphic forms. So when you consider about the crystalline amorphous form is more soluble form. This is why we have to study about the crystalline nature of the drug. When the drug is available in both crystalline and amorphous form, which form we have to choose? The amorphous form. Why? Because amorphous form is more soluble than that of crystalline form. So the persons who are trying for the competitive exams, please consider here which form will be. Many competitive exams included this question, like which form is more soluble, amorphous or crystalline form. Amorphous form will have more solubility than that of crystalline forms. Example, novobiocin. Antibiotic novobiocin is existing in amorphous as well as crystalline form, and amorphous form of novobiocin has more dissolution, and hence this is used in the marketed formulation. So in case of polymorphism, other polymorphics examples like chloramphenicol also exist in 3 forms. Again here B.Pharm is used for formulation purpose. Why B.Pharm is used in the formation of chloramphenicol palmitate suspension? Because B.Pharm is highly soluble in nature. And in some suppository bases like theobromide, there are also alpha, beta, beta prime and gamma, there are